All right, so thanks everyone for making it back after lunch. So my talk is on reversing Midway arcade audio. And so let's just get right into this because I got a lot of slides. So about me, IT monkey, consultant by day, hardware hacker by night. Interest in designing and reversing embedded systems, IC security failure analysis, arcade platforms, which is what this talk is, and automotive stuff. And you can contact me, exide31337 @yahoo.com. So what is DCS? DCS stands for Digital Compression System. So it's a sound system developed by Williams Electronics, used in Williams pinballs, casino slot machines, and Midway coin-op arcade games. So the architecture provides 6 channels of 16-bit audio, independent control over the volume, looping, and playback of each of those channels. So the distinction is it's not, I'd call it 6 voices or 6-channel polyphony, because it actually gets down-mixed to mono or stereo or whatever the hardware supports on the particular implementation. And so it can play back anything from short sound effects to voiceovers, to several-minute-long music tracks, which before that was unheard of. It would all have to be tracked or composed MIDI-style FM synthesis music. So the first pinball game to use it was Indiana Jones in '93, and the first arcade game to use it was Mortal Kombat 2, also in '93. So there's a few variants that Williams made over the years. There's the first DCS-1. So it's ROM-based mono, uses the ADSP 2105 with a single DAC. Then there's the DCS-95, which was used for some of the pinballs. There's DCS-2 ROM-based stereo, so it's got a beefier DSP running to 2 DACs, left and right channel. DCS-2 RAM-based stereo, so RAM-based meaning this one and the one underneath it, the RAM-based multi-channel. Basically, they moved to that architecture because a lot of the games started were shipping on hard drives instead of EEPROMs. So the multi-channel variant can run up to 6 DACs for a surround sound type deployment. And interesting, I think IDA supports the ADSP 2181, the bottom one. So I haven't played around with it though. So basically a quick history of arcade audio. So there's been several techniques over the years, so there's analog, which was, literally discrete components, amplifiers, RC networks, whatever, to generate the sound that way, oscillators, things like that. Then there was digital sound generator chips, so like just simple Nintendo style, square, triangle, whatever wave, sawtooth audio that way. Not sure. We'll see if I can get a clip. Is it playing or not? Nope. Is it possible to get the audio coming out the main speakers? Oh, there we go. So this was. So you can hear it's like basically blips and bleeps and Nintendo style. Then next came the FM synthesis era. Whoa. Feedback. Which was, so an example of this was Jackal in 1986. This used the Yamaha FM synthesis. So. So, pretty basic. Then it moved to sample-based systems like Outrun, which still used the Yamaha FM synthesis, but used the PCM sample IC. So, get a sample. And then that was followed a few years later by just a fancier sample IC in, for example, Turtles in Time in '91. So. So I like that one because the composition is good, even if the instruments sound terrible in it, compared to a lot of the games out there. So then, kind of related, here's Mortal Kombat 1, which did not use DCS. Same thing, it used the Yamaha with a sampling chip. So let's, this one. Oop. So you can hear it's kind of tinny, gross, FM synthesis characteristic sound. After that came Super Street Fighter 2 Turbo, for example, again using Yamaha but with the Q sound DSP. And then, just for reference, Street Fighter 3 Third Strike in '99 used a 16 channel, so 16 voice, but 8-bit sample IC. So we'll do a demo of this.
Fighters ready. Engage.
So you can hear the voice is kind of the sound. The voice clips are kind of scratchy because it's 8-bit sampling or whatever. And then finally, kind of related to this talk is Mortal Kombat 2 came out in '93, and it was the first game using DCS, using the analog devices ADSP 2100 family, no Yamaha, like no FM synth, just everything on the DSP. So we'll do a demo of this. Oop, where is it? There.
Jax. Johnny Cage.
So already, we'll do one more for good measure.
Round 1, fight.
So the thing to notice when you're listening to the music, the drums, it's not some wavetable or like, AW32 where it's pulling a drum sample. This is actually composed music where it was done in a studio, the mix was done right, then the master was then encoded. Like it was done like modern music composition basically. It's not a sequencer telling you drum hit, bass note type thing. It was actually like composed as a complete track. So, and then the final kind of era is modern PC. Like most arcade hardware nowadays is just x86 based, and it just has middleware libraries to do WAV, OGG, MP3, etc. So, all right. So how DCS works? What are the fundamentals? What is it doing? So you have an uncompressed WAV file or whatever source from a DAT tape or whatever they would have been using in the '90s. Encoded offline on a PC, so lots of the heavy lifting and the logic is all done in the encoder because the decoder is still complicated, but it doesn't need to do nearly what the encoder needs to do. The audio files are broken down into frames of 240 samples, and each frame is 7.68 milliseconds of audio. So that's a good compromise because it allows them, if you had a really short sound, you could get really tight with where you wanted the DSP engine to slice it for looping. And yeah, just having tight control over starting and stopping the sound. So the sounds can range from 1 to several thousand frames of these 7.68 milliseconds of audio. Each frame is transformed from time domain to frequency domain by 256-point FFT. So it uses a simple cosine window with 8 samples of overlap on each end, and that's simply to avoid audio artifacts like glitching sounds. So and then this resulting spectrum that you get is broken down into 16 subbands and then quantized according to masking curves and user-controlled parameters. So masking curves are curves that the audio engineers would tune to say basically, I know if there's going to be a strong note at this frequency, it's going to hide the notes underneath it, so we don't need any notes underneath there, can be discarded effectively. And then so these quantizing levels and the resulting audio data for each frame are entropy encoded into variable length packets, and then these packets for each audio file are combined with header blocks denoting the beginning of each frame and each sound, and those are stored as files that can be burnt into the EEPROM images. So it's architecturally very similar to MPEG-1 Layer 1 and Layer 2, so MP1 and MP2, which is like Sony SDDS, which is an 8-track, which is like mini disc. There was a Philips digital compact cassette, which was an actual cassette tape that had digital encoding instead of analog. Whereas MP3 is more complicated, so it's it's in the MP1, MP2 range. It's got roughly a 10-to-1 compression ratio, so that's actually pretty good for 1991, considering everyone else was just really doing those 4-bit or 8-bit sampling, short samples on those sample IC chips. Now, my comment would be, after looking at all this, I think it'd be very difficult to make an encoder. So if you wanted to make your own sounds for your old MK boards or pinballs or whatever you wanted, due to the missing masking curve logic, the entropy coding logic, and the quantizer behavior that was in the encoder, in that PC software. So you could do it, probably, but I would imagine the audio quality would be likely poor, because you'd be stacking a bunch of hunches and guesses of what you thought, how you thought the encoder worked on top of each other, and it would probably come out terrible, is my guess. So here's the overall block diagram of what the DCS architecture looks like. So you've got the actual game CPU/GPU, which is got a bidirectional I/O channel to the DSP. The DSP can access the sound ROMs, which contain program code and the actual audio data. And then it's got a connection to external SRAM, just because the DSP itself had very limited on-chip RAM. Then the DSP uses a serial connection to the DAC, and then the DAC has voltage output to an op-amp, which does low-pass filtering and preamp. Then that goes to a 20-watt audio amp, which goes to a mono speaker for the earlier mono revision. So here's a little bit of the actual details, but it's TI TMS 34,000 series, regular 1 meg EEPROM, an ADSP 2100 family DSP, 3 8K SRAMs, and then an 1851 16-bit serial audio DAC. So don't worry about all the words on here. This is kind of just the first page of the data sheet for the DSP. Some kind of interesting things to note are this is the 2105, and there's no on-chip ROM, E2, flash, or cache. It pretty much boots from RAM externally, or from external ROM, whatever's mapped into the address space, because it hangs all its address lines out externally and just goes from there. So kind of some of the weird stuff about DSPs, it's 24-bit program data bus, 16-bit data bus, because it's Harvard, so it's got code and data separate buses, 40-bit multiply and accumulate unit, which is 16 bits, and 8, a 32-bit barrel shifter, and it's got a data address generator, which can generate modulo, like circular addressing, so you can easily create circular buffers in hardware, and it can also do bit reversal. So let's say you have 11000, it will generate 00011, the reverse of that, which is used for a lot of DSP algorithms, like even in the IFFT. And other than that, this particular implementation is clocked with a 10 megahertz crystal. And I think that's all the relevant stuff there. So here's what the program memory map looks like. The first chunk is can be mapped in from external boot memory. So that's the internal program RAM. There is a chunk further up that's external program RAM, and that region is shared with the data RAM bus. And then I've noticed that the DCS code just really doesn't map too much map anything beyond this one FFF address, so the rest is unused. And then the data memory map is, so the DSP has a bunch of different chunks with different weight states that can be configurable based on how slow or fast or the needs of the type of external memory you hook to, which is common. And so nothing terribly crazy here. It maps in those 3 external SRAMs. There is a 1000 hex 1000 word bank window, so that's a 1000 hex word into the physical sound EEPROMs, and then you use the bank select register underneath to actually map in the next 1000 words. And there's the TMS CPU I/O latch. That is used to receive sound commands from the game CPU saying, play this grunt, play this scream, play this knife sound, play this background music, stop, loop, whatever. and then it's got the DSP's got its own internal RAM near the end, followed by some system registers. Now, this, probably won't go through all this, but this is just kind of a map of all the kind of interesting areas that the code itself uses for its own constants and things like that. The DAC playout buffer, we'll cover that later. And when the TMS CPU, the game CPU, writes to that I/O latch, it will fire IRQ2 on the DSP, and that's how the DSP knows there's a new command waiting. So here's kind of my hybrid diagram showing how the DSP actually clocks the audio data, the time domain digital audio data out to the DAC. And so it's pretty much serial clock, transmit frame sync, which is connected to the latch, I think it's the latch enable pin, which actually, the DAC is double buffered, so it takes the shift register and transfers it over to the parallel register once on that LE signal. The data pin, and then there's just the crystal in there. And kind of trivia to note is the DAC clock is running at 500 kilohertz. So 500 kilohertz divided by 16-bit samples gives you 32 kilohertz sampling rate. So this thing is running at 3/4 CD quality, basically. And then the output of the DAC goes to the preamp from pin 9. So the sound ROMs themselves, they're, like I said, they contain the code and the actual compressed audio. There's no encryption or obfuscation in this era. You can pretty much remove them from the PCB and dump with a parallel EEPROM programmer, like your Willem, Zeltec, or your own design, whatever you want. Nothing too crazy there. So the Wolf series of hardware from Williams, which is what MK3 runs on, uses 4 of these 1 megabit by 8 bits, so it comes out to be 1 megabyte UV EEPROMs. So 4 of them would give you 4 megs total, as you could see from here. And with a 10-to-1 compression, it would yield you basically 40 megs of uncompressed audio, which is pretty good for 91, basically. And so the organization of the sound ROMs, the bootloader, which is, there's a stage 1 and 2 code. The rest of the running program code and miscellaneous data sits in the U2 ROM, and I'll cover that in the next slide, at these offsets, followed by compression dictionaries, which are basically the Huffman tables used to actually decode the variable length data from the stream. Lookup table entries, which are actually where the DSP first goes when it's commanded to play a sound. It needs to get a first pointer, and there's a lookup table of pointers, and then followed by sound headers. So that first tuple or pointer points to the sound header points to the frame header, because remember, a frame is 7.68 milliseconds of audio. And then finally, other stuff in these EEPROMs are the actual compressed audio itself. So later games, as I said, use IDE hard drives, and they copy the code and relevant data to DRAM. So I don't know what the partitioning or file system of the hard drives looks like. All I've been looking at is the physical ROMs. So here's the U2, which is the first sound ROM. So it's, like I said, it's got all those data at these various locations, but it's pretty much all that stuff in the first one, and then right near the end is where you get the frame headers and the compressed audio. And all the following ROMs will just be compressed audio with more frame of audio. All the code and stuff stays in the first one, and all the rest, all the audio itself goes in the other 3 ROMs, for example, or 4 or 5, how many the game has. So the important thing here to note is that the DSP looks up a pointer at hex 4040, which contains the value 4048. Then it takes the sound command from the CPU, multiplies it by 3, and then adds it to this 4048, and then that gets you the position in this ROM of the lookup table entry, which itself is a 3-byte value pointing you somewhere down to the sound header section. So as I said, the other 3 ROMs are just audio, pretty much. And the bank switching, like I said, there's a hex 1000 word bank window. And writing to the data memory bus in location 3000 will map in a different bank. So the upper 8 bits of that 16-bit word are modulo 4 values, so 0, 1, 2, 3, and then if you go like 4, 5, 6, 7, it's equivalent of 0, 1, 2, 3 ad nauseum, and those select 0, 1, 2, 3 selects U2, U3, U4, and U5 ROM, respectively. And then the lower 8 bits of that word selects the what offset to go to in the actual ROM. So here's a few examples here, just showing you that 1 in the upper 8 bits goes to U3, 2 goes to U4, 3 goes to U5, and then the last 2 digits basically map in the offset in that physical ROM. So we'll quickly speed through some of these. This is just a quick history. This is the very first, this is the TUnit is the board on the left, and it typically came, for everything except more MK2, came with Yamaha FM synthesis chip, whereas MK2, since they had a modular ribbon cable design, they just designed a new board with, there's the DSP sitting right in the middle. And now they bolted on basically streaming compressed audio to the existing motherboard. And this is just a close-up of that board on the DSP board on the right. So there's the 2105, 3 SRAMs, the actual sound ROMs, and there's more of them in MK2 than in MK3, but that's likely just because they're smaller EPROMs than the ones used in the later games. And a giant heatsink for the 20-watt power amp going to the speaker. So here's the Wolf unit, which was MK3, Open Ice, NBA Maximum Hang Time, WWF WrestleMania, a few other games. So there's the 4 sound ROMs up in the upper left corner. The DSP is kind of to the right of it. There's 3 SRAMs over there. And then in the upper right corner is the DAC, the preamp, and then the giant heatsink in the upper right is the audio amp. So just a closer view of the DSP and the 10 megahertz crystal, and just a closer view of the DAC and the audio amp section. Here's Killer Instinct, which shipped with a hard drive for the graphics and animations and transitions, but curiously the sound in this game was still on the 8 yellow stickered EPROMs in the bottom corner. So the DSP is right in the middle here, and same thing, 3 SRAMs. This is a later Seattle board for NFL Blitz 2000, for example, where it shipped on a hard drive. So there's no sound ROMs anymore. It's completely whatever the file system is, and these later systems were backed with DRAM instead of SRAM, and I guess would transfer from the drive to DRAM, and then the DSP would run everything out of RAM. And here's World Cup Soccer Pinball. Williams made a different spin of the board. It looks similar to the MK2 board, but it's not quite the same. Same deal, DSP, the sound ROMs up at the top. I don't know what the second heat sunk chip is there. So basically, with this DCS system design, kind of the parameters or the attributes about it, and this could hold true with almost any audio compression system. What do you want to attain with your design? So with DCS, early versions were mono, then stereo, then multi-channel in terms like surround sound style. The polyphony or voices was 6 all the way from the beginning, at least in the MK3 stuff I was looking at, it's 6. So it can play 6. It can keep track of 6 sounds at the same time. So a music track, a voiceover, a couple hits at the same time, whatever else, and then it down mixes all that to mono, for example, and then puts it out the one speaker. Sample rate, 32 kilohertz, 16-bit. The IFFT is done in hardware. 16 sub-bands, 16 buckets, basically. The quantization is variable number of bits based on the sub-band, so it can change how many bits it wants to put into each frequency bucket based on if it's high frequency and you're not going to hear it, it may allocate it 0 bits. So the entropy encoding, in this case, I think it's Huffman coding, or if you want to extract that to the more general case, prefix coding. So that's basically where you'll have values in RAM. The upper byte is a length, and the lower byte is the actual value. So the length basically tells the the decoding code to advance the bit stream that much length, and then start looking for the next code word in the data stream, the next symbol. Bitstream generation, this is where, so basically there was those lookup table entries, those 3-byte lookup table entries pointed to sound headers. Those sound headers point to frame headers, and then the frame header includes how many, the first frame header includes how many frames to follow, and then it contains these subband quantization values, which is effectively like how many bits each bucket should get, and how many subbands are actually in this frame, because if it doesn't need all 16, it won't use them. And then followed by the actual compressed audio data. And then finally the ROM image creation. So this contains the DSP bootloader, init code, program code. It's got those compression code word to symbol mapping dictionaries, as well as the compressed audio itself. And then this data is split into images and then burnt into the actual EPROMs. So a quick compression background based on those subbands and quantization I was talking about. So again, the FFT is used to convert the time domain samples. So that's your amplitude on your Winamp visualization, to frequency domain, which is the kind of the equalizer style bar depicting each frequency bucket. The subband coding, like I said, is used to distribute bits based on the frequency bins. High frequency is less perceivable, so you need less bits. And then finally, the last step is a lossless entropy coding, Huffman, where it's doing those Huffman table lookups, is used to pack those samples into a variable length data stream. And this graph just kind of shows you the different kinds of compression technologies. In this case, it's using Huffman in some for some aspects. It's using subband frequency domain, and it's also using Fourier transform. So basically, by identifying what can and can't be heard, audio compression discards, basically it's chucking information that can't be perceived by the human ear. So if you know that signals are below a particular amplitude at a particular frequency, that they're not audible, you can hide that quantization noise from your brain. And a tone at a certain frequency, like if it's loud enough, will raise the threshold in a critical frequency band around that frequency. And I'll show you this next slide. And then this masking effect, temporal masking, is the masking that occurs when a sound raises the audibility threshold for a brief interval preceding and following the sound. So it kind of fools your brain that you won't hear the stuff nearby it that's quieter. And this is all in comparison to traditional lossless methods like zip or RAR, which don't discard data at any stage of the game, because obviously you don't want to unzip a file and it's completely mangled from what you zipped in the first place. So they have good integrity, but they won't compress obviously as small. So here's kind of the masking effect, where a really loud, a distinct, intense sound will basically raise the threshold, and then anything under this dashed line you won't hear. So you can basically start tossing these masked tones or frequency components without affecting, the brain won't notice it too much, basically. So this is my take on the DCS encoder. You basically have the uncompressed audio samples coming in, 32 kilohertz, 16-bit. It does the frequency mapping FFT transformation. Then that goes into the quantization and subband block. And this is fed by the perceptual model. So this is what's missing in terms of you trying to make an encoder so you can make your own sounds. You don't know what their masking curve logic is and how they generated their Huffman tables and stuff like that. So that was all done not in real time on a 486 class machine back in the day. So it would take hours to generate the compressed files, whereas the DSP had to do it in real time. So there's way more work involved in the encoder, obviously. And then so that goes to the bitstream generation, which gives you your variable length bitstream. And it's basically the reverse, the other direction. You read in the bitstream, use your compression dictionary to start pulling the quantization values and the actual audio itself samples out, and then you transform them from frequency domain back into time domain with inverse FFT. So this is just a quick screenshot. It's probably hard to see of my life for the last several weeks, which is the amazing built-in debugger in the debug build of MAME. So, because once you have the sound ROM, the data off the physical sound ROMs I don't think this project would have happened if I had to write my own ADSP 2100 disassembler and a TI TMS disassembler and whatever. It's like it was too many layers of overwhelming. So I just use this, and it's pretty cool. You've got your program memory bus, 24-bit over here. You've got your 16-bit data RAM values up here, and then you can see the 40-bit multiply and accumulate unit over here, and the 32-bit shifter. So, yeah, and I think I already mentioned, but I do believe IDA has support for the later versions of the DSP family, but I haven't played with it. So the quick summary of this slide is the DSP boot and initialization process. Effectively, this thing goes through a couple stages before it actually starts running, and it's doing things like installing IRQ handlers, enabling the IRQ that responds when the handler that responds when the game CPU talks to the DSP, clears internal RAM, replaces the reset vector, and then issues itself a soft reboot. And then at that point, it comes up again in stage 2, moves some more areas of memory around, wipes the buffers that get played out to the DAC with the actual uncompressed audio. Yeah, wipes more memory, configures the serial port hardware going to the DAC. So this is effectively the main code loop for the DSP code. It's what it's spending 99% of its life doing. It will sit there processing pending TMS sound commands, so that's from the game CPU. It'll do some quick sanity checking, and then it'll calculate that base pointer, that 4048 plus 3 times the sound command, which will allow it to index the EEPROM and find where the rest of the sound data is located, basically. Then it parses that sound header more fully and the frame header. Then it decompresses the frame into a block of data memory. So that's simply undoing it's entropy decoding the data. And these last two processes are per channel, because remember, or per voice. Sorry with the confusing terminology, but per voice, like it can play 6 things. It can keep track of 6 sounds at the same time. So it's doing these processes in a loop before it moves on for each channel or each voice. And then finally it does the IFFT, so it converts that frequency data back to time data, scales it down, because when you do an IFFT, the samples get louder, basically. That's just the nature of running the process. You got to scale them back down. You apply that windowing and overlap data functions to smooth the data out between frames so you don't get audible glitches. And then you actually fill the DAC buffers, which eventually get clocked out to the DACs, and the DAC turns them into voltages which we can hear through the speaker. And then finally, it does one last loop to calculate the per-channel gains, like the volume gains, and respond back to the TMS. It is bidirectional, although the overwhelming majority of the time, it's not sending any data back to the game CPU. In this case, all these memory locations in the brackets beside them, these are referencing Ultimate Mortal Kombat 3 code. I apologize, I didn't include the actual revision of the game, which version it is, but it's whatever the most popular one was. So, doing kind of a deeper dive into those commands, the first step, processing the commands, wipes the contents of RAM, checks if any new commands have come in, and stores them into this circular buffer. IRQ2 fires when the game CPU talks to the DSP. Handler validates the command, make sure it's not anomalous, stores it in the buffer. And just for trivia, the TMS's address at this location is mapped to the DSP. So if you're ever looking at the game code on the GPU CPU, this is its address of where it sends, and then that pops out on the other end in the DSP. So yeah, and it basically finds and stores the pointer to the valid sound header by walking those trail of pointers in ROM, and then it checks for more pending sound commands, because this thing can handle several sound commands at the same time if they all come in one after another. So the next stage is finding and parsing the sound and frame headers. So like I said, it does that three times the sound command from the CPU. goes in ROM at this location, finds this value, this 18183, then walks to 18183, which is the sound header, and you get this string of bytes here. The interesting stuff is in red is the pointer to the frame header, which it has to walk, and then this 0147, which is hex 147 frames in this sound to follow, or that the sound is comprised of that many frames. Good. And so the sound header itself, once it walks to 104754, which is the U3 ROM and at this offset, all these strings of orange are basically, the important point is the number of these orange bytes, not necessarily what contents there are. That tells you how many subband values are in this frame out of a possible 16 frequency subbands. And if it's 7F or FF bytes, it means stop parsing this frame, we're done with the subbands. So after this, in the frame header, once you've looked up the frame header, you'll have the subband dequantization values per each subband compressed, and then also then finally the compressed audio data itself comes after those subbands. So the remaining frames after that frame header consist of dequantization values and compressed audio. There's no more headers, and yeah. Then you're decompressing the frame. At that point, you're entropy decoding it. Yeah, a lot of these are the specific locations for reference, but yeah, and then you finally jump to this location which just wipes some counters and is ready to handle another sound if it needs to. So effectively what's happening is it's actually accumulating all of the frequency domain samples for all 6 channels at the same instance. So what you'll get is you'll have like music, scream, and Scorpion's harpoon. Those values will all be accumulated on top of each other, and eventually they'll have to be scaled down because it does all of its mixing in the frequency domain basically, and then per subband below, so per frequency bucket. So it's kind of an interesting way of doing it. Then finally they're almost done, you do the inverse FFT. The first couple of iterations are unrolled in their code, and that's where that bit reversed addressing is used for accessing the FFT's twiddle factors are called in scrambled order. This is all standard FFT, nothing fancy, nothing secret they're doing. And then it's got to scale those samples down because that effect of doing the IFFT makes them too loud. So yeah, there's just a graph. I've got to keep moving. This is just what it looks like in memory once you do the IFFT. Then the code waits for the serial port to finish clocking out the existing sample buffer, and copies the new samples in, keeps to the standby buffer, which it'll switch to eventually, and then start clocking those out. It keeps 16 samples for overlap, and then when it's time, the serial port treats that standby buffer as the active and starts clocking out. So it's just a continual fill, empty cycle. And if there's no sound requested by the CPU, basically the DSP will calculate a bunch of IFFT, it'll run the IFFT on zeros, copies those zeros to the buffer, and then clocks those out. So it's just continually running even if a sound isn't requested. So here's what the frequency domain data looks like if it's graphed, which is garbage looking. Here's what the time domain, so this is an actual decent looking waveform. Here's your leftover 16 samples that it keeps for the next frame's overlap. And then here's the smoothing cosine window. So, and then the last step is it just did just calculated the gains and then responded back to the CPU, like I said, if it needed to. So yeah, that can trigger pinball lighting, mechanical flippers, things like that. So conclusion, basically using a low-cost DSP allowed high-efficiency, good quality audio compression algorithm to be accelerated in hardware. It provided roughly a 10-to-1 compression ratio, so the game audio could still be squeezed into EEPROMs instead of having to think about CD-ROMs or hard drives, but they eventually did go to hard drives. Competing systems were using FM synthesis, and low-quality short playback didn't sound that good. And then the DCS system basically allowed the musician the freedom to compose like they were in a traditional studio. They could use whatever instruments, anything they wanted, because it was just compressed audio at that point. So I think I'm out of time, but I just had some sample clips from Street Fighter and MK3. Do we have any time? We're out of time? Okay. So that is everything, and thank you everyone for sticking around.
Here we go.